Hello and welcome back to the CCENT journey with me, Ryan. In this next section, we're going to continue with the routing part of the ICND1 or CCENT, and this time we're going to put all of our efforts and focus on static routing. In the previous video, we had a look at the differences between static and dynamic, and then prior to that, we looked at why we need routing to begin with. In this video, we're going to drill down into static routing. We're going to talk about some of the caveats and some of the features it offers us. And then we're going to jump in and actually configure some static routing. This video will be long, it'll be about 30 minutes plus, and if you do find it helpful, please do like and subscribe. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. We're going to start with the PowerPoint presentation, and then we're going to move into hands-on. A few things we need to cover. First up, next hop IP can't be an interface unless it's an MBMA. So this is something that I focused on in the last video. I said that when we go to create a static route, we first of all go into the config terminal, we use the IP route command, and then we specify which network we're trying to reach. Let's say 192.168.0.0. We specify the subnet mask of that network. Let's say in this case it's a /24. And then we say if you want to get to the 192.168.0.0/24, go to, and then we insert our next hop IP address. And I said it always has to be an IP address. However, that's not always necessarily true. So what do I mean by that? Well, first of all, let's address what an MBMA is. MBMA stands for non-broadcast multiple access. Now, if you think about Ethernet, we've had a good discussion around the history of Ethernet and what it allows us to do, and I'm sure that we can all agree that if you have a switch and you have multiple PCs connected into that switch, then we can send broadcast traffic into the switch and it will be sent back out to all the other ports, let's say if we're doing something like ARP. Because this is possible, we consider this a broadcast access medium, or sometimes referred to as a multiple access network. Because unlike any other technologies, Ethernet, we may have one wire connected to us, but there could be multiple devices connected to the actual Ethernet network, the layer 2 network. Because of this, it's called a broadcast multiple access network. A non-broadcast multiple access network, hence the N, is the opposite of a broadcast network. And if we think of this like a router connecting directly to another router, here, if they were to run Ethernet, then just like explained, it would be considered a broadcast network, because this router doesn't necessarily know that there's only one device on this point-to-point link. So because of that, it still does the ARP process if needed, and it still treats it as a broadcast segment. But if we had, let's say, another link across to a router, and this link was, let's say, a serial link, and for those who don't know, serial links are represented normally via lightning bolts, then we can consider this a point-to-point, both physically and logically. Because over the serial link, you don't run Ethernet, you run protocols like the HDLC, which is the high level data link control, PPP, which is the point-to-point protocol. These protocols don't support any kind of broadcasting, and they only can have one person at either end of that. Because of that, it's considered NBMA. Now, 9 out of 10 times in your networks, you're going to be running a broadcast technology, in this case Ethernet, and if you are, then you cannot put an interface as the next hop here. It will work, but there's some problems with that. In an ideal situation, if you're running an BMA, a broadcast media or medium like Ethernet, you need to make sure you're popping in the IP address of the next hop, not your local interface. If you're running a serial, you can put in the actual local interface. So why is this important? It's important because if we think about broadcast networks, in this case Ethernet, it runs certain protocols to help us resolve addresses. And we know so far in our studies that we've talked very extensively about ARP, and we know ARP is used because there could potentially be multiple people on the network, just as shown up here. And in order for this to actually work, we need some sort of process, some sort of broadcast process to find the correct resolution for the layer 2 address in order to do some kind of unicast communication. Well, let's say we were to put the interface here. Let's say, for example, we had two routers. These two routers were connected in a point-to-point link. And then behind here is the internet. And from the internet, we have a 0 route as a default gateway being advertised. And on this router, we create an IP route to say, if you want to get to the default gateway of all zeros, subnet mask of all zeros, go to the interface FA00, which is my local interface here. What this tells the router is that every single network that I do not have a more specific route for is directly reachable out this interface. And because it's directly reachable out this interface, the router will perform an ARP for every single unique destination that you try to route towards. So if you went to 8.8.8.8, this router will send an ARP onto this link for the 8.8.8.8. If you went to 8.8.8.9, a new ARP would be generated. And since this is a default gateway and you might have thousands of people in your network, it won't be long before this router here, its ARP cache gets too big, and in turn traffic is dropped because there's no memory left for the other processes running on the device. If we were to correct this by not putting the local interface, but by putting the next hop IP, let's say between this link there was the 10.0.0.0/30, .1 was here. If we put in the 10.0.0.1 is our next hop, then it would say perform an ARP, get the MAC address for my next hop, and every time you're trying to get to a destination, let's say the 8.8.8.8 again, then I won't need to ARP for that. I would just send it to my already resolved next hop, and it will stop this memory issue. Now if you go and put a default route or a static route and point it towards your local interface, the router will tell you that it's not recommended for broadcast networks like Ethernet. It should only be done on serial links or technologies such as PPPoE, which is point-to-point protocol over Ethernet, which is actually considered point-to-point, and therefore you can point the next hop to the local interface because there is no ARP process. And the reason there's no ARP process is because it's an NBMA network type, which in turn means there's only one possible person at the end of the link. Even though your routers are connected like this, if they're running Ethernet, this router or this router does not know that there's only one device. It doesn't know whether there's a switch in the middle, a hub, and whether there's 100 devices connected off it. So because of that, 9 out of 10 times we are running Ethernet, and because of that we have to always ensure the next hop is the IP of the remote device and not our local interface. Otherwise you're going to run into this memory problem with ARP doing its correct job in trying to resolve the networks because it believes it's reachable outside the directly connected interfaces. Now you may be thinking this may cause a black hole in traffic, because if we had a particular device ARPing for each destination, surely it won't get a response because 8.8.8.8 doesn't live on this link. Well, by default, Cisco routers are set up with something called proxy ARP. And proxy ARP essentially means if this router was to ARP on the link for a destination that this router knows about, and he knows about it through the default gateway, then this router will respond on the behalf of 8.8.8.8 and say, hey, when you build your layer 2 frame, put me as your MAC address and I will get you to the destination. And this is called proxy up. So proxy up is where someone else who knows how to get to the destination responds on the behalf of the destination in order to get you off the local segment. And the reason this is used by default is because in some older network designs, this is a valid behavior and it's a behavior we want to achieve with some sort of traffic engineering. Nowadays, we use other protocols instead of proxy up, but because proxy up is on by default and because you can set a static route to your local interface, you can end up in this problem where you have a router with thousands of ARP entries and eventually the device will fail over because of running out of memory. If we're using Ethernet, we point it to the next hop IP. If we're using serial, we point it to the local interface. There is a possibility when you can use technologies such as tunneling or point-to-point over Ethernet, which is acceptable for static routes pointing towards your local interface. But 9 out of 10 times, especially at the CCENT ICND1 level, you're mainly creating static routes to your next hop. Next up, we have AD. The default AD of a static is 1, but it can be changed. And if it's changed, we can then use something called a floating static. So at the moment, we haven't talked about routing decisions, but very briefly, a router will always prefer the longest match. If the longest match is the same, it will pick the lowest AD, and if the AD is the same, it will pick the metric inside that AD. So say, for example, if we learnt 2 routes from the routing information protocol, it will then pick the one with the lowest hop count. Keeping that in mind, quick example, let's say we have 2 links across to a router, and one of these links are running RIP. Let's say it's let's call it a different color here. Let's say this link here is running RIP, and the link at the bottom is running static. And let's say there's subnet X and subnet Y. Well, in order for subnet Y to get to subnet X, by default, it will prefer the static. The first check the router does is who has the longest match. And because the static and RIP is both advertising the same network and with the same network length, i.e. a /24, so then it will go on AD. The AD for a static route is 1, RIP it's 120, and because 1's lower, the static route wins. What we can do is we can increase the static route to a higher AD, let's say 130, and because of that, the path to RIP will be preferred. And now what we've created is a floating static, because this static route is in the actual routing process and it's valid because it can get to the next hop, it can recurse, but it's not going to be used because some other process, in this case RIP, is being preferred because of the lower AD. If this link were to go down, then the RIP route will be removed from the routing table and the only route left would be the static, and as such the static route will then be installed and the traffic flow will then go across this link instead of the top link. And having that static route in the background but with a higher AD is referred to as a floating static, and it's used in very basic failover scenarios and basic engineering designs. Another option we have for static routing is something called the permanent option. Now, this is something that I don't think is actually in the ICND1, but I think it warrants a 5-minute discussion. And essentially, the reason it warrants the 5-minute discussion is because it helps you understand what recursion is. If we have 2 routers that are directly connected, and let's say in this router we have an IP route statement for a network that is reachable over here, and let's also say that that IP route statement is then being advertised into RIP off into a bunch of other routers out in the network. Well, in order for this static route to be valid, the next hop, which is here, needs to be available inside the routing table. Which means if we think about this router would say, in order to get to network, let's say 192.168.0.0/24, go to 10.0.0.2, and let's say this is 2, let's say this is 1, and let's say the 192 network is over here. Well, in order for this static route to remain in the routing table, it does the lookup to find where 10.0.0.2 is, and it says, I know how to get to 10.0.0.2, I found it outside this interface. Well, if this interface were to go down, then it can no longer get to this next hop, and as such, the static route can no longer recurse to the interface, and it's removed by the routing table. And when it's removed from the routing table, it's no longer advertised into the RIP domain or any other domains by OSPF, EIGRP that it may be advertised into. So because of this, we can use the permanent option to say, regardless of what happens over here, what happens with this link, always advertise this static route to the rest of the network. And as such, the rest of the network and all the other domains will always be able to reach that network towards the router in question. Now, depending on what happens when it gets there, for example, let's say that there's a router in the RIP domain that decides to route up in order to get to this network. Obviously, if the link's down, the communication will fail. However, the path to that destination will still be advertised regardless of the criteria here and regardless of the recursion if the permanent option is used. So we can use static routes to create default routing. So we have an internet out here, and our provider is giving us a router, and on the edge of our network, let's say this is where our demarcation is with the provider. On the edge of our network, we have a /30 with the provider, .1 over here with .2, and then we have the rest of our network. Maybe it goes downstream towards the core or distribution layer and so forth. What we want to do is create some sort of static route to capture everything and send it towards this next hop. And if we've only got one exit out of our network, then static route may be a viable option. So in order to do that, we would simply do IP route from global config, but instead of specifying a remote IP, we do all zeros for both the remote IP address, the remote network, and the remote subnet, and then based on the IP address of the next hop interface, which in this case, let's say it's the 10.0.0.1 network. It will get all of our traffic to this next hop, and then they will have some sort of default mechanism to push it up towards the internet in order to reach any other destination. So static routes can be used to create default gateways outside our network. Some examples of some static routes. We've seen this in the previous videos. You can see this is the syntax, and it's done from the global config. So from the standard iOS, we go to enable, and then from enable, we do the config T, and then we can type in the IP route, the destination network, the destination subnet mask, and then the next hop IP if this is that broadcast media like Ethernet. Here's a good example of that. Here's a very bad example of someone doing a next hop of a local broadcast interface, in this case a fast Ethernet interface. And here's a good example of someone doing it on a point-to-point interface, such as a serial link, which is where that is actually allowed to take place. And then again, verification, we do the show IP route with the static keyword to show us the routing table with only the static entries. We can do IP route to a specific destination. So we can do show IP route 192.168.0.10/24, and it would tell us everything we need to know about that route. Or we can say show us the running config, pipe to include any words that have IP route in it. And this will show us in the running config anything that has the IP route command in, which will only be the static routes. Okay, so I have set up a network just like we've seen previously. We have the 172.16.0.0 over here, .1 with the host and 254 as its gateway. We have the 192.168.0.0/24 over here, again, .1 as the host, 254 as its gateway, and then the two routers are connected using a /30 in the 10 network. If we look up router 1 and we put across its routing table, we can see, just like we have talked about in the previous videos, router 1 only knows what it's directly connected to. So it knows gig 00 and it knows gig 01. So what we need to do now is add some kind of routing, in this case static routing, to tell router 1 how to reach the 192.168.0.0 network. Now in order for a static route to be true, it needs to be able to recurse to the next interface, or recurse to the egress interface. So what I mean by that is if we were to do a static route on router 1, point it to router 2, but this link between the actual two routers were down, then the static route will not work. It will be in the running config, but it will not be installed into the routing table, because when router 1 goes to look at its next hop and notices the next hop is 10.0.0.0.2, the interface will be down to that network, and as such the router will not be installed. In this case the network is up, therefore we can add the static route and it should be installed into the routing table as expected. So we go into config terminal, show IP route, put in the network, which is the 192.168.0.0/24 subnet mask 255.255.255.0, and then as explained previously, we have to put in the IP address of the next hop. We don't want to put in gig 00. The router will now do a lookup to say, how do I get to the 192.168.0.0? It says I know how to get there, and I'm going to get there by using the next hop of 10.0.0.2, and then in recursive logic, how to get to 10.0.0.2? I know how to get there out of gig 00. Now the recursion's in place and we're happy, we can go ahead and try to ping the destination. So let's skip straight down and try to ping the actual host of 192.168.0.1, and rightly so, it's able to respond back. Now if we go to PC1 and we check our reachability on PC1, we know that PC1 can ping its default gateway. So the question now is, can PC1 ping across to the remote host? And the answer to this is no. So why is this failing? Router 1 can reach the destination, but PC2 cannot. Well, it comes down to who's sourcing the traffic. When router 1 creates its data, the source IP of that data is going to be the interface gig 00. And because of that, source becomes 10.0.0.1. Well, router 2, which is the default gateway for this PC down here, knows how to reach the 10.0.0 network. Therefore, it works as expected and we get full end-to-end reachability. Router 2, however, does not know, if we go to router 2, how to reach the 172.16 network. So let's expand that, and we can see it doesn't have it in its routing table. As such, when we're inside the network of 172.16, reachability cannot be achieved. So in order to do this, we need to make sure router 2 has a path back to the 172.16 network. So again, config T, IP route, and this time we do 10.0.0.1, which is routers 1. And again, if we now check the routing table, we have the route here that says I know how to get to the 172.16/24. It's via the 10.0.0.1, and 10.0.0.1 is inside this /30, which is directly connected out of gig 00. If we now go to PC2 and we rerun the ping, we can see that end-to-end reachability is now achieved, because this router 2 knows how to reach the network behind router 1, and router 1 knows how to reach the network behind router 2. Now if we were to go to router 2, and let's say this interface gig 00, we actually go ahead and shut it down. Now when we shut it down, even though we've shut it down on router 2 side, if we go to router 1 and look at the routing table, what you'll find is the route itself is actually being removed, because the recursion can now no longer take place. So we look at the routing table and hit show IP route. Notice the 192 network's not there, and nor is the 10 network, because the interface is in an up-down state, so it's not viable to be installed as a connected route. And because we have a static route that goes through that interface, any static routes that need to go to that next hop, because that next hop is no longer in our table, we can no longer use that static route, but of course it will still show in the running config, which is here. Now if we were, I don't know if this is supported inside of Packet Tracer, to put the permanent, no, so if you were to put the permanent option on the end of the static route, then even though that recursion has failed, it will still be installed in the routing table. That's something, like I said, is not in the CCENT, not in the ICND1. However, it's good to know how recursion works, because 9 out of 10 times, if you created a static route and you've created it correctly, then it's normally the recursion that causes it not to be installed in the routing table. What we can do though, is previously explained, increase the distance, and this is the administrative distance. So by default, the administrative distance is 1, and we can see that by looking at the routing table. So if we scroll all the way back up to when the routing table was actually installed correctly, you can see the route was installed with a distance of 1. Here we can increase the distance, let's say to give it the AD of, let's say 10. We go across to this PC, go across to this router, sorry, and then we can go back into the interface, bring it back up, switch back to this guy, and then when he installs the route in his routing table, you'll notice that first of all the administrative distance is changed to 10, whereas previously was 1. And this is how you would actually increase the administrative distance to be less preferred than another protocol, and when you do that, it's called a floating static, something that we will test out and demonstrate when we get into our dynamic routing section of the course. Last thing is the default routing, and stay with me, I know we've already gone through quite a lot already in this video. If we were to get rid of the static route that we put in previously, by typing no, and then we're going to copy paste, and that will get rid of it out of the routing table. And this time we're going to say, if you want to get to any network with any subnet mask, go to the next hop of 10.0.0.2, and then we looked at our routing table. We can see that the 192 network is not in our routing table. However, we do have a static route that points towards the 10.0.0.2, which knows about the 192 network. So if we go back to PC2 and check reachability, you'll notice that it will still work. Now it took a while here because the ARP cache most likely timed out, or the switch's MAC address table, but we can see that reachability is still working end to end, and the reason for that working end to end is because router 1 receives a request in order to get to the 192.168 network. It doesn't know where that network lives, and it hasn't got a specific route inside its routing table, or what we sometimes call a longer match. So because of that, it uses its shortest match, which is the default gateway, which is, I don't know where 192 is, therefore I'm going to go to my default gateway, which is router 2. Router 2 gets it, looks inside its routing table, and says, guess what? I do know how to get to the 192.168.0.0.24, and passes it to the relevant host. And because it knows how to get back to the 172.16 network, it knows how to get back to whoever sourced the traffic. Okay, so that's all we've got time for in this lesson. We carried on with our static routing topic. We jumped into understanding what a non-broadcast multiple access actually is. We said these are things like the point-to-point technology that runs over serial links and HDLC, which is the complete opposite of the broadcast medium like Ethernet, and why as a broadcast medium we have to specify the next hop IP and not local interface. We then went into recursion. We understood by going on to packet tracer itself, looking at the recursion process and disabling the next hop and seeing how that affected the routing table. We then had a look at AD. We increased the AD and verified that through the routing table. And of course, we looked at the static routing end to end. We had two networks that were completely separate to one another, and then we done static routing on both routers in order to obtain full end-to-end reachability between two end hosts in different networks. I hope this video has been informative, and I'd like to thank you for viewing, and if it has been, please do like and subscribe.